In this video, we will be going over the basics of a manual lensometer, including how to use the instrument to read the power of a lens, where it is appropriate to read the lens, and how to write out the prescription. Lensometers can be used to read the power of an ophthalmic lens and even hard contact lenses. It can also locate the optical center of a lens, which can be used when fabricating eyewear. Let's review some parts of the lensometer. The eyepiece is the portion of the lensometer that you view through. The piece is able to be twisted to set the appropriate optics to the user. Note what happens to the black circles and numbers as the eyepiece is turned. The chrome knurled sleeve is a twistable collar underneath the eyepiece. When twisted, this moves the straight black line within the lensometer viewing area. It's most commonly set to either the horizontal 180 line or the vertical 90-degree meridian. Continuing down the lensometer is a prism compensating device. This is used to manipulate the illuminated lines that you see within the lensometer. Its purpose is to aid in finding prism in a specific spot of the lens. The prism compensating device is composed of a scale and a knob. The knob can twist, which will move the lines inside the lensometer, as well as the scale. It can be completely moved so that the knob is pointing in a different direction. Usually we have it pointing up at the 90 degree or on the side at the 180 degree marks. Twisting the knob will move the illuminated lines closer and further from the knob itself. The lens stop and the holder, as well as the lens stage and its lever, help us place the glasses in the lensometer accurately. The concave inside of the lens will rest on the lens stop. Think of it as though the lens stop is where the patient's eye normally is. The holder helps rest the lens in place, freeing up your other hand. The stage can be moved with a corresponding lever so that the eyewear is level itself. It is important to make sure that the lenses are both touching the stage when reading toric lenses. The power drum is on the side of the lensometer, and the axis wheel is in the back. They're both used to identify the power of the lens. The axis wheel will, when twisted, move the illuminated lines around, and the power drum will clear them up. Two other common parts on lensometers is the locking level, which is used to keep the lensometer raised to the user's height, and the on and off switch. Inside the lensometer we have the reticle and the illuminated lines. Different lensometers may look different on the inside, but by default the lines are usually thinner for the sphere lines and thicker for the sill lines. The first step in using a lensometer that is new to you is to calibrate it. Do this by placing a white piece of paper at the lens stop to help see the reticle inside. While looking into the lensometer, twist the eyepiece counterclockwise to blur up the numbers in the circles. Doing this relaxes the user's eyes and minimizes any error that our eyes can unintentionally make by overfocusing. Slowly turn the eyepiece counterclockwise. As soon as the reticle is sharp and clear, stop. Do not keep going and then go back and forth and bracket to find the right clarity. That is when your eye will overfocus and cause problems. The next thing to do is look at the eyeglasses you're working with. The main type of ophthalmic lenses are single vision, line multifocal, and progressive edition lenses or PALs. Single vision and progressives are very similar looking superficially. Line multifocals should be easy to spot. Line multifocals will have a clear, demarcated segment that should be noticeable right away. The lower portion has more plus power in the segment to help the patient read. Single vision lenses have the same power throughout the entire lens. Plus lenses will make everything larger and will make the patient's field of view smaller. Minus lenses minimize everything and make the field of view larger. Just look at how many of the boxes in the graph paper you're able to see through those lenses. Progressives will not have a noticeable segment on the bottom of the lens, but will still have more plus power there to help the patient see up close. Notice the way the lines at the bottom of a progressive lens distort versus how they stayed straight with single vision lenses. Some progressives with a smaller add power may be more difficult to see the distortion. You can view a straight edge like the side of a table, a ceiling tile, or the edge of a piece of paper through the lens and slowly move the eyewear up and down. If the line bends at the bottom, it's a progressive. If you're still not sure it's a single vision or a progressive, you can use the lensometer to measure a higher portion of the lens versus the lower portion of the lens and look for any differences in overall power. When inserting eyewear into a lensometer, make sure that you take care not to scratch the lens. The lens holder can be slippery and can slam down hard on top of the lens. It's also important to consider what portion of the lens you are measuring through. Different areas can read differently. For example, the reading portion of the lens will have a different power than the distance, and each spot on the lens itself will exhibit different amounts of prism. Once you've determined where you're reading, place the inside of the lens carefully against the lens stop. Adjust the stage so the glasses rest appropriately on both lenses or touching the stage itself. There are two common places we read lenses at. The first is called the major reference point, or MRP. This is found by placing the eyewear on the patient and marking the lens when the patient is looking straight ahead. When placing the glasses on the lensometer, the MRP is placed right where the lens stop is. This will allow us to identify the amount and direction of prism that a specific patient endures in any given set of eyewear. The second way to set up glasses in a lensometer is to set them such that the middle intersection of the illuminated lines is in the exact middle of the reticle. This allows us to identify the optical center, or OC, of the lens. In other words, the place where light that travels perpendicular to a lens travels through the lens and is not impacted. If the MRP and the OC are the same, then the patient's frame is set so that the OC is aligned with their eyes and they will not experience any prism. When the glasses are not exactly set the way that they should be, then prism will be induced. To find the power of a lens at the spot that's being read, we first twist the power drum into the plus power until the lines are completely blurred. Next, slowly move the drum into the minus power while moving the axis wheel in the back. Look for the thinner sphere lines to clear up first. If the thick lines clear up first, then twist the axis wheel 90 degrees and the sphere lines will come into focus. You can rotate the axis wheel back and forth and bracket it to make sure that you have the right axis. This is harder to do when the difference between the sphere and the cylinder powers are minimal. Once in the appropriate range with the sphere lines coming into focus first, move the power into plus to relax your eye's focusing system again, just like we did when we calibrated the equipment with the eyepiece. Slowly move into minus and stop as soon as the small sphere lines are clear. Record the total power for the sphere. Keep moving into the minus so that you can find the thick cylinder lines. Once clear, record the total power here. Don't forget to record the axis that was found as well. If you did this backwards and the cyl lines were cleared up first, the resulting prescription would be in plus cyl format. We will see what this means in a second. Repeat the same thing with the other lens. If both the sphere and the cyl lines clear up at the same time, then the lens is spherical. To write out the prescription that we just found, we write the exact total sphere power in the sphere section. The cylinder power is found by noting the movement from sphere to cylinder. This will be a negative number if you identified the sphere lines first when moving from plus to minus. It would be a plus cyl if it was the cylinder lines that had cleared up first. The difference from the sphere to cylinder power in a spherical lens is 0, but we do not write 0. Instead, we write ds, which stands for diopter sphere. Also note that each number representing the power of the lens will have at least one digit before the decimal and two afterwards. The axis number should also have 3 digits long and can be anything from 1 to 180, where we never use 0 as an axis. This nomenclature is important to minimize any errors. Here's an example of the same procedure using a set of lenses that has a higher amount of cylinder power to it. Note that the sphere and the cyl lines are not as identifiable at the same time. It's much easier to accurately identify the axis when the powers are very different like this. The same process is used to find the power of the lens as we did previously. To find the add power of the segmented portion of a lined multifocal, we read the top of the glasses, just like we did before. And then we'll go ahead and move the eyewear so that the lensometer is reading through the segmented portion. The most accurate way to read the segmented portion of a lens in a lined multifocal is to move the lens so that the front of the segment is placed against the lens stop. This requires moving the glasses completely from the lensometer and turning it around so the concave portion of the lens is actually facing the user. After identifying the top, the distance, and then the segmented portion, record that and look at the differences between the two. The difference between the distance and the near is the add power itself. Make sure you're comparing the same lines from the distance to the near. In other words, do not look at the sphere lines in the distance and then compare it with the cylinder lines in the near portion. Reading prism that a patient experiences can be done when we have the lenses appropriately placed at their MRP. Prism will shift images viewed through the lens in a certain direction by a certain amount. The first thing to do is look at the intersection of the illuminated lines in regard to the center of the reticle. If the intersection is located above that center, then it is base up. Below is therefore base down. If the intersection is located to the side, then it's a little bit more complicated. Consider this. If it is towards the right of the center, let's call that base right. To figure out if that's in or out, look at the glasses in the lensometer. The glasses should be looking straight at you, so base right in a right lens would be nearer the inside of the lens, nearer the nose. Therefore, that is base in. If it was the left lens, then the right side would be on the outside, near the temporal side of the lens. So this would be base out. To read prism, begin by placing the eyewear so that the MRP is against the lens stop. We're going to clear up the illuminated line so the intersection is noted. This can sometimes be difficult to do when there's a larger amount of cyl power. In those cases, it may be necessary to quickly go back and forth to help identify where they would cross if they were both clear at the same time. Note the position of where the intersection is. The reticle will help you identify the magnitude of the prism, while in that direction will help you figure out the actual direction of the prism. In this example, the intersection is 2.5 prism diopters, and the direction is towards the right. Looking at the glasses and the lens stop, the right side of this lens is on the outside. Therefore, it's 2.5 prism diopters base out. Now we can use the PCD to determine the prism magnitude. By twisting the knob, the intersections can align with that center. First, in this case, we need to move the PCD to the side at the 180, and then twist it until that intersection is in the center of the reticle. Here we know that it is 2.5 as the scale says that, and it was originally base out. That has not changed. If we move the prism compensating device just a little bit and the scale reads, say, 1.5, inside it should say 1, because the sum of what is shown on the reticle and on the scale of the PCD is the total magnitude of the prism. When there's complex prism with both horizontal and vertical prism present, the prism compensating device knob can be very helpful to identify the magnitude of each direction. Here, We'll go ahead and identify one direction at a time, but we need to first identify that it's base down and base left. We'll move the PCD knob until those illuminated lines cross at that horizontal midline. The scale reads 2, so 2 base down. Now we can go ahead and move that PCD so that horizontally we can identify what the prism magnitude is. First, we need to use that chromed knurled sleeve to move that midline vertically. Here we move and twist and we get another 2. Reading progressives is an entirely different beast. There are laser markings inside progressive lenses that we have to identify. We can do this by holding the lenses up to the light and looking just slightly off the light and noting the little markings that are in there. There's a number, in this case 22, and then there's a little circle in this case where we want to mark up the lens itself. Temporally, that number will correlate to the add power, and that marking there should also have a matching spot on the nasal side. The other thing to note on the nasal side is this little symbol. These are very difficult to see, but the easiest way to identify these is just looking slightly off and using indirect light to find them. Mark up both sides of the lens. Once the lenses are dotted up, use an appropriate progressive fitting chart to mark up the fitting cross. Some progressives will have a different fitting cross height in relation to where the lenses get marked up. To make sure you are marking up the lenses most accurately, identify the progressive using the symbol seen earlier, and then the manufacturer's specific chart to mark up the fitting cross. With the dots aligned to the cross, mark the cross, and you can optionally mark the dot below and the circle above it. You'll want to do this for both lenses. The fitting chart is also great for determining the PD, or the distance between the fitting crosses. For progressives, the fitting cross should be at the patient's MRP. That's how the eyewear is actually made for them. This is done by placing the lenses face down on the progressive marking chart, and the fitting crosses should be on that horizontal scale. Use the red chevrons in the middle there to align the eyewear side to side. The fitting height is shown under the lens, and then the monocular PD on that scale. When placing a progressive lens in a lensometer, we need to consider if we are reading the distance portion of the lens or if we're looking for prism. The top portion within that circle is the distance reference point, or DRP. This is where the distance portion is identified. The near portion was determined earlier with that temporal laser marking number. If the glasses are set into the lensometer directly under the fitting cross, then we're reading the prism reference point, or PRP. This is where the prism of the glasses is found. It's important to note that a lot of progressive lenses will have yoked base down prism, as they may have gone through some prism thinning. I mentioned writing the circle above and the dot below was optional. This is because the placement can be done by using just the fitting cross. To read the DRP, move the fitting cross to be at the bottom of the lens stop, and for the PRP, it should just go on top. Effective power of a lens is considered when the lens is moved away from the position that the lenses were originally made to be in. When a patient's prescription is determined, it's found to be at a specific distance from the patient's eye. This is the vertex distance. If that distance changes, so will the power experienced by the patient with the same glasses. The same is true when the glasses are tilted. To demonstrate this, let's first clear up the illuminated lines. We'll then go ahead and move the glasses. First forward, away from the lens stop. Note how the illuminated lines blur up when this happens. That's because the actual power, or the effective power in this case, changes. If we tilt the glasses forward, the same thing will occur. This is called panoscopic tilt. The power experienced by the patient overall increases, more in one meridian than the other. If we do the same thing and tilt the glasses to the side, this changes the wrap, or the face form of the actual glasses. The same thing happens, but it affects the other meridian instead. It is critically important to make sure that the measurements taken to make glasses is 100% spot on, or else the wearer may get unwanted prism in their glasses, which can cause difficulties for them. It is also very important to consider the way each frame sits on the patient prior to the eyewear being made. If the glasses are not made with these considerations, the effective power of the glasses may cause the wearer to have an improper power experienced in their glasses. I hope this video has helped you understand how to use Lensometer better and maybe gave you some pearls of wisdom that you may or may not have originally known. Thanks for watching.